Yes, sir.
Good. Okay. Can you see the screen? Can you see the screen?
Yes, sir.
Look at problem number 1. This came in first class test last year. Yeah, I suggest that if you want to take 30 seconds break, you can take, but please bring a copy and a calculator if you have at home. Then the maximum use of this class can be made. Please get a copy and a calculator. Then you can try something. Did you hear what I said? Yeah, hello, can you hear what I said?
Yes, sir.
Yeah, so please get a copy and a calculator. And come back. We'll start after 2 minutes. Otherwise, you don't have it, you can leave it. If you don't have it around, but you should be having it. You are at home. So we'll start talking after 1 minute. In the meantime, I can use this. So let me project this here. The question has to be projected. So read it carefully. For an instrument, the maximum positive value of its only modifying input causes a 5% change in sensitivity to the measured input. So that means that, why is this? This is a problem. This is a problem. So that means that, suppose that let us recall the equation. O is equal to O array. What happened here? Something happened. So O is equal to Ki plus Ni plus Km plus, well, you can absorb that plus A into Ni if you want. Km Im plus Ki Ii. This is the equation, right? So what is the nominal sensitivity of the instrument? It is this. So it says that, and what is the sensitivity of the instrument? In this instrument, Ni is assumed to be 0. Is it stated in the problem? Consider the instrument is ideal in all other respects. That means there is no nonlinearity. That means there is no nonlinearity and there is no interfering input. All other respects, the instrument is ideal. So the sensitivity changes with respect to the, so it is sensitivity so with modifying input sensitivity is this. So it says that Im max Km Im max is equal to 0.05 K. This is the first equation that you get. Do you agree or not? Do you agree? Can you hear me? Hello, can you not hear me? Huh? Achha, I have to call by name. Nitish Kumar, can you hear me?
Yes, sir.
So somebody should say yes, sir. Otherwise, it's difficult. So, do you get this equation or not? You have to respond. Otherwise, it's very difficult to take online classes. Unless you respond to me, it's very difficult. I can't see you. I can't see your face. So if I don't get a feedback, it's very difficult to progress. So did you get this equation or not? Is the question. Nobody got the equation from the problem? I think here is the problem. I'm just trying to interpret the problem. Tell me when somebody gets it. Not getting this simple equation. Wow. Eh? Let me ask. Nitish Kumar, you didn't get the equation?
Yes, sir. I got the equation.
So then why are you keeping quiet? You got the equation.
Yes, sir. I was I am thinking ahead that what could be the possible solution of this.
So is there anybody who has not got the equation? Is there anybody who has not got the equation? Madhu Kumari Meena.
Yes, sir. Yes, sir, I got it. Sir.
Yeah.
Yes, sir, I got it.
See, when you say something, you immediately ask for a feedback. You said, sir, when I am asking for a feedback, nobody is giving it.
Sir, can you show the properly? I have not read it. Like I read only the first one.
Yeah, what about the others? So two samples are good. Sumed Lodi. Sounds like a kindergarten class. Yeah, Sumed Lodi.
Yes.
Yes. What yes? What am I asking?
About the question, I got that.
So what is your answer? Wow, what a beautiful class. Yeah. Let's see. What is your answer?
You were asking about the equation. I forgot.
What is your answer? What is your answer to my question? Yeah, hello Sumit. What is your answer to the question?
I did not get the question.
Thank you. Manvendra Singh Kushwaha. Manvendra Singh Kushwaha. What about Moinak Ghosh? Nice smile. Moinak Ghosh.
Yes, I got the question.
So really, I mean, you don't like to respond. Eh? You don't like to say yes, I got it. Nobody likes to say that. Eh? So you know, the lesson I got is that from now on, I'll ask to a specific person, and then assume that similar responses are available with others. I think that's the way to go forward. Okay, so we go back. So then what is the next? What does the next part say? So what does this statement say? So what is the maximum value that of IM that can occur under this situation? Can you tell? The maximum value of IM that can occur. Can you see the marked part in my slide? In my
Yes, sir.
Thank you. So if you can see the marked part, then can you tell me that under this situation, what is the what are the limits of IM that can occur? If a Gaussian variable, random variable drawn from a distribution with mean mu and standard deviation sigma occurs, then what are the limits of that variable? Yeah? Any response? Nobody wants to say anything? If a random variable of mean value 0.5 Imax and standard deviation 0.01 Imax is drawn, what is the largest value of that variable possible?
Its value at mu.
The mean value is mu and the standard deviation is sigma.
So largest value possible is its value. I mean the value of normal curve at the mean.
So what is the value? Sanket Kanto. I don't know how you pronounce your name. Sanket Kanta. Can you hear me? Sanket? Hello, Sanket. Yesterday, some IISc professor was telling me, I was telling him that, you know, we have not done enough experiments in the online classes. We are just going there and we are just speaking. This is not the way to take online classes. So he was telling me that, no, we have done some experiments. We have made classes more interactive. And I'm failing at that. Sanket Kanta. I don't, maybe he's not present. Hardik Mohanty ji. Can you hear?
Yes, sir. Yes, I can hear you.
So my question, did you hear my question?
So actually, I lost my internet connection for the last 2 minutes. So
Okay,
the normal question I couldn't hear.
very good. Who heard my question? Lekhraj Parihar.
Yes, sir.
Did you hear my question?
Yes, sir. Means we have to find the limit of IM max from the deviation.
Yes. So what is the limit of IM max when this is given? We'll go slow, but let's try what the IISc professor said is good for classes. So what is the value of IM max when in this problem? From the information that is given in the blue marked part, what is the value of IM max? Maximum, not IM max. What is the value that can occur under this situation? During a measurement, the modifying input is assumed to be a Gaussian random variable of mean 0.5 IM max and standard deviation 0.01 IM max. So what can we assume to be the maximum value of the input?
Sir, I think it's, yeah.
You think it is?
Sir.
Good. Come on.
So I think 0.51 because mean is 0.5 and deviation is 0.01.
So this is interesting. So nobody here knows that if you are given a random variable of a mean and sigma value, how to calculate the limits of that variable approximately is not known to the class, known to anybody in the class. Is that a safe assumption to make? Then because this is beyond instrumentation. This if you don't have that understanding, then it's somewhat surprising to me. But we'll try to talk about it. So if you have a random variable, what is this Gaussian distribution? This Gaussian distribution, what are the axes? The axis is, this side is the value of the random variable x, and this side is the probability density function px. So, and the random variable plot looks somewhat like this. So actually a Gaussian variable extends from plus infinity to minus infinity. If you ask a mathematician, then the mathematician will say that if you are giving me a Gaussian random variable, then the maximum value of x will be plus infinity. That is strictly true. But if I am asking this question to an engineer, then the engineer will know that if this is mu, then between 99% probability, and if this is mu minus 3 sigma and this is mu plus 3 sigma, then the probability of that variable, which is the integral under the curve, the integral under the curve from plus infinity to minus infinity is equal to 1, because from plus infinity to minus infinity, px dx is equal to 1. But if you integrate it from mu minus 3 sigma to mu plus 3 sigma, then this value comes to be about 99.7. If you change the limit to mu plus 3 sigma and this one to mu minus 3 sigma, then this number becomes almost 0.997. So you can say that under this situation, this plus minus 3 sigma is a safe limit. You can say that the variable will occur within this limit. You may have heard about, those who read things about, other, let's say, industrial production, manufacturing. You may have heard of a word called Six Sigma. It's a very popular, manufacturing management term. So Six Sigma is even higher. You are talking about mu minus 6 sigma and mu plus 6 sigma. So you are talking about, probability of 0.9999 several nines. It's almost 1. So that means that it's almost certain. So 6 sigma means certainty, but typically we can take it as mu minus 3 sigma to mu plus 3 sigma. So that covers almost full probability. Then now can we say what will be the limits of this? If you are given a Gaussian random variable, then you can safely say that the variable will, in 99.7% of the cases, the variable will lie between mu minus 3 sigma and mu plus 3 sigma. Although mathematically there may be an odd chance that it could go beyond that. So now what will be the value? Did you get what I said? Was it clear or not? Rather, is there anyone who did not understand it? What about Yash Harkawat? Yash? Yeah, hello Yash. Yash may not be there. So who else? Let's talk about Abhinay Japesh. Are you there?
Yes, sir.
Did you get what I said?
Yes, sir. Now got it. Like, I was not sure about this mu minus 3 sigma to mu plus 3 sigma, but now it got it.
Right. Good. I hope that is a similar situation with others. Others, Sony?
Yes, sir.
Good. So we can progress. So now we are here. So that means we got a maximum value of IM that can occur under this measurement situation. It will be 0.53 IM max. Now it says compute the limits of instrument output for an input value of half the full scale input range in terms of the full scale output range with more than 99% confidence. So this 99% confidence comes when I'm saying more than 99% confidence. From this word, I understood that we have to take plus minus 3 sigma. Because plus minus 3 sigma gives more than 99% confidence. If more confidence was required, then we would have had to consider a bigger range. But with 99% confidence, plus minus 3 sigma is okay. So now my question is very simple, but you have to interpret the terms. The whole exercise that we are doing and will be doing for the next few classes is whether you can interpret an instrument related statement, whether you can understand what it means. So that is the whole exercise that we are going to do in the next few classes. So now coming back to the whiteboard, and let's rub off this Gaussian business because we are done with it. इसका क्या हो गया? Wow, it's not rubbing. Why is it not rubbing? Clear canvas. No, I don't want to clear canvas. But this has become hard. It's not rubbing. Intelligent software again. Okay. So now my output, let's write, okay. So I have to go here. So my output is what? Again, it's K times 0.5 I max, not IM max. Because it said that our input is full scale input range, 50% of full scale input range. So that's why 0.5 I max plus Km IM max, but I am not K plus Km. I have just now determined what is the maximum value of IM max. That is 0.53 IM max into 0.5 I max, that is I. This is now my output, maximum output in this situation. So it is now this, sorry, this is fine. So this term I know is 0.53 into 0.05 K. So that is 0.0265 K into 0.5 I max. This term I got from here. Just multiplied 0.05 by 0.53. So it is K into 0.5 I max plus 0.101325 25. Looks like 25, yes. 0.5 into 0.0265 is 0.01325. That's good. K times I max. So it is 0.0 0.5111325 K times I max. Now Omax, what is the maximum value? What is the full scale output range? Omax, or the full scale output range, OFS, is equal to K times I max. Because it is the full scale output occurs at full scale input, and it is the nominal value. So we can assume that when you are considering the ideal output, ideal full scale output, we can consider that the modifying input is 0. So now, this is the answer there, that this is equal to, O is equal to, maximum value of O is 0.51325 into O, Fs. This is the right. So is this clear now? So one value we have obtained. Okay. So the maximum value of the compute the limits of instrument output. So the maximum value for IM maximum of modifying input in terms of the full scale output range with more than 99% confidence we have obtained. So it is going to be 0.51325 times the, so 51.325% of the full scale output range. When the input is 50% of the full scale input range, then the maximum value of output under that kind of an modifying input will be 51.325, and you can consider the minimum value by considering mu minus 3 sigma. So the minimum value is 0.5 minus 0.03. So you can now consider 0.47 IM max to be the value, and you can calculate the whole thing. So this is an interpretation of the modifying input. Is this clear?
Yes.
Wow. Thank you. Thank you. It really feels good when somebody says, yes, sir. You cannot understand my feelings. If I ask you 3 times and I don't get an answer from 37 people, it feels like a rejection. Believe me. It feels like you are not happy, you don't want to attend this class, you don't care. It feels all these things. Thank you, Shankar. Battala Sai Rohit, are you there?
Yes, sir.
Samjha? Did you understand
Yes.
what I said?
Yes.
Yes, just now. I mean, I explained the problem. Could you get it?
Yes, sir.
Wow, wonderful. I am happy because that's why I am laboring. Chinmoyi, did you hear me?
Yes, sir.
Could you get it?
Yes, sir.
Wow. Now we can move on to a new problem. So I'm just trying to, now we went through a book, chapter 2 and 3. And now we are trying to see whether, based on our understanding, whether we can, given a situation, whether we can interpret the data. That's what we are trying to see. And it's a very important, with respect to the course, I think from a user point of view, that's one of the most important competencies that are targeted in this course. That if you read a data sheet, you will be able to make some sense out of it. It's very important. All right, let's move on. Let's see what the next problem has. The next problem looks like a little more. We'll not go to the next problem because the next problem is much more elaborate. Probably we'll put the next problem in the assignment. It talks about ADXL 335 is a commercial acceleration sensor. manufactured by analog devices. So this problem, which was given in the exam, talks about interpreting this sensor specification from the real data sheet which is issued by the company. So, but we'll probably put it in the assignment sheet for this year, and you can try it. Right now I will not try it because it will take too much time. You first have a look at it, then we can talk about it. So it's also not to scare you, but it is also to tell you that such questions will come in the exam. Almost certainly you will get a data sheet of a commercial sensor and some questions will be asked about it. So if you do not know how to interpret the data sheet of commercial sensors, then you will not do well in the first class test. So I'm just trying to motivate you. Okay, so let's go to another problem. Let's see, I have got many such problems. So let's do another problem. What about this one? Okay, assignment 01. This was last year's assignment, right? So let's read the assignment. We will change the assignment this year. We'll put some new problems, but just look at the assignment which was given last year. So can you draw this? Can you understand this? We drew a block diagram for instruments, which had a, remember the block diagram of instruments? It's like this. I think where is that? Where is my blackboard gone? Whiteboard. I killed it. Yes. Oops. Why did I kill it? Okay. So you probably remember the block diagram. Let's go to a new board. So remember the block diagram of the instrument. First there is the sensor. Then there is a signal conditioner, sensor, signal conditioner. Then there is a signal processor. Then there is an application module. This is a typical block diagram of a sensor. So this question asks, a qualitative question, the functional components in instrumentation system, or classify. Oh no, this question is about classification. Major classes of functional components in instrumentation system. Justify an alarm for indicating high water level in a tank. So an alarm is which of these four boxes that I had drawn? Which of these four boxes that I had drawn? No, what is the question? So classify the following objects into the major classes of functional components in instrumentation system. Yes. So an alarm for indicating high water level in a tank. So which one of these four blocks that I had drawn here is the alarm? We have these high water level things in these domestic automatic pumps. It is there in my house in Kolkata. So the pump is the underground tank, which is on the basement of the house, has a submerged pump, and it has a level sensor. Similarly, the overhead tank on the roof also has a level sensor. So when the overhead tank level is low, it sends a signal to the system, and the pump starts to pump water from the underground tank to the roof tank. So the question is this. So this is an instrumentation system, obviously. So what is this alarm is which block? It's a very
Sir, I guess alarm is not part of any of these.
no,
Alarm is
it is a
independent.
okay. So good point. So he is saying that alarm is not a part of any of these. That's nice for saying this. Suppose I say that the alarm is here.
Yes, then it's fine.
Then it's fine. Good. So we have answered the first question. Thank you for saying that again. You know, I'll tell you, we all in a class. I mean, you come to a class, right? You have got up at 8 o'clock and you have come to the class. Why? I've already told you that, you know, I mean, attendance does not matter. So you don't have to bother about deregistering you, because this is standard student psyche. Before the deregistration date, till that time there will be some attendance, and then after that it will fall. It happens every year. You know it and I know it. But I'm telling you that you don't have to bother about it. Just write the exams and submit the assignment. That's enough. If you choose to learn. But for example, this class, if you don't come to this class, your probability of doing well in the exam will reduce. That's why you have come to this class. Now, if you want to take benefits of this class, what should you do? So, we all think, first of all, we have fear of public speaking, talking in front of 30 people. Next thing is that I think that, oh, if I say something wrong, what will happen? What will happen? Nothing will happen. But if you don't talk about it, if you don't sometimes talk about it, then you are not taking enough from the class. So therefore, if you have a doubt, you should have the confidence of raising your hand. I think you are mature enough. You are going to be an officer very soon. So let's talk about the second one, extension wire. These are very carefully chosen. Examples to confuse you, so that you really can not confuse, to make you think hard. So the answer is not obvious. So now, but it will be difficult for you to answer this question because you don't know what is an extension wire. So we'll skip this question. You don't yet know what is an extension wire. It has not been covered in the class. You can think about it later on. Actually, these extension wires are, because if you have to run thermocouple wires, are very expensive. For example, if you have a platinum thermocouple. So, but anyway, we'll skip this question. Let's talk about this one. So we just talked about it. So you see the strain gauge, we just talked about it in the last class. So the strain gauge resistance change happens due to strain and due to temperature. You don't want the resistance change due to temperature as a reading. You're not measuring temperature. So the question is, how can you compensate for the temperature effect? We talked about it in the last class. So can you tell me which this dummy strain gauge is part of which block of those four?
It's a signal conditioning.
Yes. Thank you. It's part of the signal conditioning because what is meant by a dummy strain gauge? It is a strain gauge which is placed close to the actual strain gauge because it has to sense the same temperature, but it is not fixed to the body. See, strain gauges, how do they sense the strain on a member? Because it is fixed to the body using some sort of adhesive, so that when the body stretches, that strain is transferred to the gauge. But a dummy strain gauge is not fixed to the body. It is placed close to the active gauge so that it senses the same temperature, but it is not connected to the body. So it does not sense the strain. And it is placed in some arm of the bridge. So it's like this, as we had, probably you can imagine that. I'm just drawing a simple case. This is the bridge, this is V supply, and this is your output E0. And this is the active strain gauge, and this is the dummy strain gauge. So now you see that if there is no strain, suppose, so then, but there is high temperature or value, change in temperature, then this will change by delta R due to temperature, and this will change by the same delta R. So the bridge ratio will remain unchanged. So there will be so there will be zero output, even if the temperature changes, right? So this is what is done with the dummy strain gauge, and so it is part of the signal conditioning. Thank you very much. Great. I'm happy. Then this one. Actually, these are a little difficult for you to answer, I understand, because you don't yet have okay, fine. So we'll skip this question. We'll see it. So this is a manometer used for differential pressure sensing across an orifice plate flow meter. So you don't yet know what is an orifice plate flow meter. We'll study it. This question also will skip, because briefly describe measurement systems where the sensor is in contact with the medium. Can you, in your experience, have you seen a sensor when the sensor is in contact with the medium?
It's a thermometer.
Good. Fantastic. That's very easy. What about the next one? Have you seen a sensor which is not in contact with the medium?
Temperature.
Temperature. So what sort of but a thermometer is also measures temperature. First of all, temperature is not a sensor. Which sensor are you talking about?
Sir, infrared temperature sensor.
Yeah.
Infrared temperature sensor. Yes, infrared temperature sensor, laser position measurement. These are all sensors not contact with the medium. Signal conditioning circuits are at a distance from the sensor. Signal conditioning circuits are integrated with the sensor. Signal conditioning and processing circuit are absent. Can you say a sensor where signal conditioning and processing circuits are absent?
Light detector.
Light detector.
Yeah.
Light detector. There is a
Like photodiode, something like that.
so photodiode will require power supply, right?
Okay.
Sir, a clinical thermometer.
Yes, clinical thermometer. Correct. Clinical thermometer, normal. Oh, what do you call it in Hindi? I mean the common scale, or the spring scale. What do you call a scale in Hindi? I mean weighing scale. Something wajan, is it? Nobody knows. Somebody must be knowing. Huh? Why? Who knows? How do you call a weighing scale in Hindi? Adarsh Soni ji. Hello.
Sir, I'm not sure.
You? Are you Hindi speaking?
Yes, sir, I'm in this speaker.
You're not sure? My God.
So
Okay.
Taraju. Sir,
Huh?
sir, do you mean Taraju?
मुझे पता नहीं. I don't know the word. I don't know. Taraju. Okay.
Yes, sir, it's Taraju.
Who said it's Taraju? Somebody said with confidence it is Taraju.
Sir, Ishan.
Huh?
Sir, it's Taraju.
Taraju.
Yes, sir.
अच्छा. छोटा ऊ या बड़ा ऊ?
Sir, बड़ा हूँ.
बड़ा ऊ. Okay. That's unusual. Anyway, let's not deviate. Okay, so the next question, let's see. Yeah, the next question is, we'll do the next question. Can you do this one? Can you look at this? Problem number 3. there are three systems. One is a thermocouple is giving some output, then it's going through an amplifier, and then it's going through an indicator. The worst. Oh, somebody's calling. Just a moment. Yeah, Kishore, I'm in a class. You are, yeah. Right. It is about that purchase committee, na?
तो चलती रहती है चलो
अच्छा ठीक है after the class
क्लास
after 12 अच्छा ठीक है okay fine correct okay yeah tell me sorry let me again silent it ये silent करने का चक्कर में मैं भूल जाता हूँ don't remember to switch it on okay बोलिए tell me somebody was telling something. First of all, the worst case error specifications are given. So worst case error specification means we can assume that the error is within plus minus 1%. So if the error is plus minus 1%, then what is the nearest approximation to the overall worst case error? Can you say that? Assuming the errors are independent and zero mean. Look at the problem. Is this problem solvable? I don't know whether this problem is solvable. I think there is some. I am beginning to think that I have set the problem in the assignment sheet last year. That's true, but I am now thinking that this has some. What is the problem? Let me. Do you think there is enough data given here? Neither the amplifier gain is given, nor the thermocouple sensitivity is given. So do you think it is only thing is that it is an indicator instrument? So the overall sensitivity, that means the gain of the thermocouple multiplied by the gain of the amplifier multiplied by the gain of the indicator is 1. That is given. So is it not? So let's try. So the first kya hai? So what is the, suppose there is a temperature T, then thermocouple output is what? Thermocouple output will be, let's say the thermocouple has some sensitivity. So K thermocouple into T. Typical sensitivity is 40 microvolts per degree centigrade plus 3% is the, so plus error in the thermocouple. This is now going as input to the amplifier. So it is, what is the amplifier output is K amplifier times KTC T plus ETC plus E amplifier. And what is the, suppose the indicator gain is I, so this is going to the indicator. So it will be Ki times Ka times KTC into T plus ETC plus EA bracket close plus EI. This will be the final expression. So this, let's rub this off. देखो ये freeze हो गया. The problem So now, so this is given as, so first of all, this, oops, okay. KTC into T, the first term. So this term is 0, is 1, because it's an indicating instrument. And then we are getting, that is the thing that we are getting. So the term, so the error term that we are getting is Ki Ka etc plus Ki Ea plus Ei. This is the term. Total error. So my question, that is why my question, that if Ki, K and Ki and K are not given, KTC, if Ki and K are given, then KTC can be calculated, because Ki, K, KTC is 1. So if Ki, K are not given, can we calculate this, is my question. That's why I got a doubt. So do you agree? What do you think? Yeah? Give some view. I think the problem looks like the problem has, do you agree with me or not? Yeah.
Maybe some additional inputs are required.
Some means what? Why do you say some? Do you agree with this expression that T at this point, after the thermocouple, this is the output, right or wrong?
Yeah, right, sir.
Then that is going into the amplifier. So this is the output, right or wrong?
Correct.
Then that is going to the indicator. So right or wrong? Correct.
That's
again.
correct, sir.
So now I get, so this is the total expression then, out of which this part is 1, we know, because it's an indicating instrument, same temperature is being displayed, so it has to become 1.
Huh.
But how do we calculate these things unless we know Ki and K? I have some doubt. So now the question is that this EA, no, there may be something. What is this EA? It is 1% of what is the question. So what is it 1% of? So if it is 1% of the full scale output, let us see, it may be, if it is 1% of full scale output, right now we are thinking what? We are thinking that it is 1% of the reading. Is it not? Right now we are thinking that it is 1% of the reading. Right? If we put 1% here, then we imply that it is 1% of KTCT. But if it is 1% of full scale, then that 1% would cause an 1% error here. So everything now will be with respect to correct. This is the good thing. There's no data missing. And now I suppose this is, but it should have said that it is 1% of full scale. It does not say one. Does it say 1% of full scale? This is very interesting. This is very interesting. So this is worst case errors of the system. What is the worst case? As percentage? No, it is written as percentage of reading already. So it is But if it was 1% of full scale, then we could have just added them, I think. Then we could have just added them, because this gives 1% of full scale error. This also gives 1% of full scale error. That means the 3% will finally translate to 3% of full scale error here for the nominal gain. And similarly, this would also translate to 1%. So then it would have been 5% if it was full scale error, but it says reading. So now we have a problem. If it is reading, then kya kar raha tha here? Did you get my argument, the thing that I was saying?
Yes,
Why
sir.
1% of full scale will simply add to all of them, right?
Yes, sir.
If you interpret, question is error 3% is not a complete statement. It is 3% of what? So if it is, I am saying that if it is 3% of full scale, then the full scale of amplifier would translate to full scale of the output. Right? Is it not? That's how the gain of the indicator has been fixed. ये क्या हो रहा है? So if it was full scale, then I could have simply said that this is also a full scale. If this error will result in 3% error in full scale, this error will also result in 1% error of full scale. And well, it is, suppose this is 1% of full scale, and this is more than 3%. So 1.03 into this error will be there, but that I'm ignoring. I'm ignoring all second order terms. But first order terms will be just 1% plus 3% plus 1% of full scale, that is 5%. Do you agree or not?
Yes, sir.
But jhamela hai if it is called percent of reading.
Hello, sir.
Yes. Sir.
It is given the percentage of reading, right? So the equation that you have written, can you show that whiteboard?
Yes.
Here you have written the output after the first sensor, that is KTC into T plus ETC. But ETC is actually the 1% of that KTC T.
Correct.
So
I've not yet defined ETC. We can define it as, we can write it as, this term, we can write it as maximum value, 1.01 KTC into T.
Yes, sir. So if we will proceed with this way, then basically we can have all those numbers, all those percentage in addition and multiplication.
0.01 KTC into T. Okay, very good. Let's have. So then I have. So this becomes now 1.01 KTC into T. Okay. So now this is, and this is what he's saying is good thought. He's saying that EA is equal to 1.03 into KA into KTC into T. Not EA, 1.03, 0.03. So now this becomes, so I substitute this, and this becomes 1.01 KTC into T plus 0.03 Ka into KTC into T.
Actually, sir, here the input is 1.01 into KTC into T. So,
here also K. So that becomes now 1.04 Ka into KTC into T. Good. So now this will be, this is here, this EI. Now this whole thing is now 1.03 into KTC into T. So the same thing I do. So now I say KI times 1.04 into K into KTC into T plus 0.01 into K into KTC into T into Ki into T, right? So now it becomes 1.05 KTC into Ki into Ka into KTC into T. So it is 1.05 into this. So it's 5% again, maximum value. Right? That's what you are saying.
Yes, sir.
Yes. Good. See? Now I'm fairly sure that you have understood. Actually, I made a mistake. I was getting, but because I didn't work out. So there's no data missing anyway.
Sir, the relation between thermocouple and temperature is not given. So it can be KT square also.
It can be KT square also. That's true.
Then the error will change. Maximum error.
Then we are not going to normally for, yeah, that is true. So that we did not. So actually speaking, we should say that whether the temperature, we should what type of model we should use for such, for each of these devices. We should actually say that. In fact, if we go to the book, so now we can go to the book and just quickly we can make a detour and principles of measurement system. If you see the end of the book problems, they will say that in each of the cases these models are given, right? So because it was sorry, error bands. Let's see. I'm just trying to go to the assignment for chapter 3. Yes. But let's go to the assignment for chapter 3. And then we'll come. Similar problems are there in the assignment. Chapter 2 and 3 you should read very well. And if you have any problems, we can discuss. Yes. So now you see that this same problem is now given like this. Read this problem, 3.1. Now it is given with more data. In place of amplifier, a current converter is given. That's fine. So now read this problem. See, now all these values are given. this problem can be solved exactly as given in the example. So you can, the mean values are given, so you can calculate the mean EMF for a given temperature, and then only C0 is supposed to be uncertain, so you have to differentiate with respect to C0 and get the first sigma square E, and then you should use sigma square E here, sigma square E in this place, and the sigmas of ambient is given, sigma of A1 is given. So all these terms, the sigma of A1 is given, sigma of delta T is given. So then you can calculate sigma square I, and then you can substitute sigma square I here, and already sigma A2 is given, so you will get the final sigma of the measured. This is the case of sigma. But if the case is, so you see there is a difference between this worst case error and this sigma error. Sigma errors are you take squares of those, and but basically you have to calculate root mean square, because the sigmas are, the sigma of three groups in series is going to be as summed up as, if there are three random variables in the equation, for example in the second converter equation there is E, which is a random variable, there is delta T, which is a random variable, there is delta TA, and there is A, which is also a random variable. So the overall variation in the random variable is the sum of, is the RMS value of the others multiplied by the gains. That is the way to do it when you are trying to calculate sigma. But when you are trying to calculate worst case, then you have to literally find the worst case. So here, everything is positive, so the worst cases are always for positive values. So here you have to find out that if this E was given as a worst, suppose this was given as a worst case, the maximum limit Emax plus minus so much, then you have to take the plus value and calculate the plus value of E, then you have to put the plus value there and the plus value here and the plus value here, because these are all additive. If this sign was negative, you have to take a minus value here. You have to see what is the worst case value of deviation from I that you can create using worst case deviations of each of these random things. So typically the worst, it is, if you take magnitude of each one of them and of the terms and you add them to get the, so if a quantity is, if y is equal to x plus z plus w, then in terms of worst case error, what is the worst case magnitude of y? It is mod x plus mod y mod z plus mod w, right? So like that. So the worst case calculations, what happened here? Yeah. Okay. So let's do some other problem. Yes, I wanted to show you this one. So I wanted to show you. So this is the thing that we wanted to see. There are some other problems given as well. This is a force balance, that closed loop sensor for error reduction. But I wanted to similar. Here you see that in some cases he has given a rectangular distribution, which is but he has given a rectangular distribution, but is not looking for worst case values. See, we just saw that if you are given a Gaussian and if you are asked to get sigma, then you will get from sigma the Gaussian and you can do RMS and all that. If you are given a distribution sigma, distribution Gaussian and ask for worst case values, then you need a confidence value, and with 99% confidence, if you want, then plus minus 3 sigma will do. On the other hand, if you have a rectangular distribution or a uniform distribution, then of which plus minus 0.5 means the worst case values are plus minus 0.5. Then the worst case values are directly calculatable for calculation of worst case by taking magnitudes. But if you have to do calculate a standard deviation with rectangular distribution, then you have to use the standard deviation of the rectangular distribution, which is h by root 3. So here you can do this in the same way, but you have to substitute this for this distribution. You have to substitute by h by root 3 if we have plus minus h here, and then do in the usual standard deviation form. That means RMS. So sometimes the way the data is presented, it can be different. But I wanted to show you another problem before we close for today. That is also interesting. Going to chapter 2. So tell me, we are trying to construct. Yeah, just a minute. No. Okay. So this problem, say 2.3. A displacement, read the problem. Read the problem. First of all, forget about this part B. You forget about the variation in output voltage with supply voltage. Let's forget that. So let's take only this part of the data. Forget the third line. Now, using this part of the data, how can we answer question A, part A? The question is that the displacement sensor is given and some calibration results are given. Actually, when a displacement was applied and output was seen, then we got these outputs. Now we have to construct a specification. So we have to construct a non-linearity specification of the instrument. So as we have seen, first of all, whenever you say non-linearity specification, you have to first say, what is the linear line? What is the line? So you have to first figure out what is the straight line that you are defining. So typically you can define the straight line in two ways. One straight line is you can do the best fit straight line. So do you know how to calculate the best fit straight line formula for this data? Can you calculate the best fit straight line for this data? Did you do it in the lab ever? I'm asking, have you ever given a set of data not using the calculator? Can you by hand calculate the best fit straight line? I think everybody possibly knows. Orko Prabha Madhu?
Yes, sir. Sir, we will. Yes, means we will put some of the points on one side of the line and some of the points on the other
How
side.
will you get the line? What is the y equal to mx plus c? How will you get the value of m and c is the question.
Sir, we have to use the principle of least square and we have to.
Yes, you have to use the principle of least square. How do you use the principle of least square? That's what I'm asking.
Okay. formula.
Do you know the formula? Do you know how to derive the formula first?
I knew it, but I'm forgetting.
Right, you knew it, but you have forgotten. It's simple. See, you don't have to remember it. ये क्या हुआ? अरे, what is this presenting? इसको can we? Yes. So let's go to a new board. It's very simple. So sum of squares must be minimized, least squares. So what is the sum of, suppose M and C, so what is the error? Total sum of square error is what? Is y1 minus mx1 plus c whole square. This is the first point ka error, plus y2 minus mx2 plus c. Second point ka error, plus, so up to the nth point. So here some 5-6 points are given. Yn minus mxn plus c. If m and c were the slopes of the line, then the error, sum of the squares of errors at each point of the end points would have been this. Now we have to differentiate this with respect to del E del m and then set equal to 0, and then you have to do del E del c and set equal to 0. This is all. Yeah, we will doing with respect to m. So what do you get here? You will get y1 square minus m square x1 square minus 2mc x1 minus c square. This is one equation. So finally, when you add them, plus dot dot dot, so you one time you get sigma yi square minus m square sigma xi square minus 2mc sigma xi minus sigma c square, which equal to nc square. This term will be sigma c square means nc square. So now you differentiate. This is the error expression. Now you differentiate with respect to n. So you will get two equations, and then if you solve in terms of the sigma yi sigma xi, you will get this. You can solve for m and c. You will get two equations, two unknowns, m and c. Right? This is the way to do it. Correct? Madhu?
Yes, sir. Yes, sir.
Right. So but while we are doing this problem, we have to first find out that इसमें कहाँ है ये इधर. So first, so we have to do the same. So first, let us but some computation. So little bit of work. So let's remove that. But what is the other straight line we can define? Other straight line we can define very easily. We can take the two endpoints. So the two endpoints. So the straight line is now it connects the point this 0, 0 point, and it connects this 358 point. Suppose we define this as a straight line. So firstly, it means that c equal to 0, and secondly, it means that m is equal to 58 by 3. Right? Yes or no? बोलो भैया बोलो. ईशान भूटानी. ईशान.
Yes, sir.
क्या ख्याल है? What do you think? यस सर बोला, फिर चुप हो गया. बोलो भैया. क्या हुआ ईशान? देखा? Are you able to hear me? Guys, somebody say yes, please. Hello. Sankalp? Sorry?
Yes, sir. Sorry, my mic was muted.
Nah, your mic was mute, but Ishan बात नहीं कर रहा. Maybe he's mad with me. So Ishan, this is funny. Anyway, कौन बोलेगा? Manavendra Singh Kushwaha, are you there? Manavendra, this is interesting. Manavendra Singh Kushwaha, very interesting. Rekhraj Parihar, are you there? See? Sankalp Srivastav, are you there? Hello. Somebody has written something in the chat box. Sir, mic problem. वाह, देखा मैंने क्या सोच रहा था कि तुम मुझसे बात नहीं करना चाहते हो. He's saying mic problem. Sankalp, are you there?
Yes, sir.
So, do you agree with what I said?
Yes. The straight line. Yes.
Straight line. So we can. So that is the straight line which is easy to define. So let's define that to be the straight line. After that, this is the key point. So suppose we define that whenever you are saying maximum nonlinearity spec, you have to choose a straight line. That is the first thing. So suppose we choose the easy straight line. That will not give you the best spec, but suppose we choose it. Be between 0, going through the point 0, 0 and 358. Now I want to understand that if I want to construct the specification of this instrument as X% of full scale or Y% of reading, whichever is greater, right? We saw that we have to construct a specification like that, and it is done. Yesterday night I was seeing, so I can show you that specifications are stated like that. Let me go to downloads. कल मैं रात कर रहा था. ये देखो Platinum RTD data sheet. Suppose, see, they will say reading error. Not here, they will say. See, the temperature accuracy they are stating. 0.5 degrees C or 0.8% of temperature. So this 0.5 degrees C is a constant number. So it can be said, it can also be expressed as a percentage of full scale, because it's a full scale is a constant number. And this is 0.8% of reading, whichever is greater. This is a commercial RTD temperature sensor data sheet, right? So this is the way. See, dekho, yeah, this is I think Honeywell. Yeah. So Honeywell is an well-known automation company. It has a lot of, building automation is an area of business, and HVAC is all the centralized air conditioning equipment. This is critical, air conditioning. Do you know what is the IIT Kharagpur is in deep trouble because of the fact that its air conditioning load is rising too much. We are not taking care of it, and it's causing us a lot of money, maintenance problems, all that. Air conditioning is a huge problem, but it's a necessity. So now we have to state the maximum nonlinearity as a percent of full scale deflection. Here it says that you don't have to do it, but suppose we want to do it. I'm okay. First, let us do the first part. This is very simple. As a percent of full scale deflection, how can we get the maximum nonlinearity? Follow? It's very simple. How can we construct a maximum nonlinearity specification as a percent of full scale from this data given, the first two rows? Very simple. Calculate the nonlinearity at each point. So if 58.3 was the slope, then at 0.5, what would have been? It would have been 29/3. What is that? Output in millivolts for 0.5. So 58/3 is the slope. So 58/6. 58 into 58/3 into 0.5. 58/3 is the slope. So at 0.5, the output according to that slope would have been 58/3 into 0.5, which is 29/3. But the output is 16.5 millivolts. So what is the error? The error is 16.5 minus 29/3. So that is the error here. Similarly, calculate errors. What is the error here? For 1 centimeter displacement, output should have been 58/3. 58/3 is how much? 19. But it is 32. At 1.5, so there is an error. So calculate the errors at each point and then take the maximum error as percentage of full scale. It's trivial. Is it clear?
Yes.
But now I am saying, I am complicating the problem by saying that constitute a specification which is X% of reading or Y% of full scale, whichever is larger. So calculate value of X and Y. Obviously, X and Y should be the smallest possible values. The smallest possible values of X and Y such that the error remains within X% of Y of full scale or Y% of reading, whichever is larger. Then how do I find X and Y? Again, very simple. At each point, calculate it as a percent. Calculate the error as a percent of reading. I calculated as I was calculating previously as a percent of full scale. So at each point, calculate the error. So calculate at the first point x1, y1. What is the x1% of reading and what is the y1% of full scale? Calculate x2, y2, xn, yn. Then takes the then you have to calculate. So now, after calculating x1, y1, x2, y2, xn, yn, what will you choose? Will you choose the maximum of all the x's as the
Probably where the error is greater, we'll have to choose that particular thing. Like, let's say the
Now,
percentage of
now you
reading is
see,
greater.
suppose at each point you will get a value of x1, x2, x3, similarly y1, y2, y3. Now, will you choose the maximum of all the x's as x and y, all the yi's as y? Will that give? Is the question. I don't think that will give. This is an interesting question. X% of, I have to calculate one x and one y. If I choose the maximum of all the x's, xi's, and the maximum of all the yi's, then obviously the error will be contained within that, but it will not give the smallest x's and y's possible. The instrument will look much worse. Let's think. I am also confused. Actually, it will be the well, yeah, this is very interesting. Let's draw a figure. Let's draw a figure. New page. One point is here, the other point is here, suppose. I have drawn a straight line joining them. Now I have a point, maybe a point here. No, this is actually not the type of data we are using. So one point here, let's say another point here, then here, here, and here, and here, suppose. Now, as percent of full scale, so this is as percent of full scale. So from here we get, this is my error E1, this is my error E2, this is my error E3. So now E1 can be expressed as X1% of FS and Y1% of reading. Obviously, you can understand that Y1 is going to be very large here. So now, using this reading, Similarly, from E2 we'll get, so we can put this EI, and from EI we'll get X1 per these two readings. Now we have to find out an X% of full scale and Y% of reading from all of this. So first of all, the X% of full scale, the smallest X% of full scale, we have to choose. So choose, because the full scale number is fixed. So choose the, if we choose the smallest X% of full scale, choose the smallest of Xi. As X% of full scale. Because if we don't choose the smallest of Xi, since the full scale value is constant, so obviously this X% reading, it will not match, but it need not match actually. If we choose the smallest of Xi, then smallest or largest? No, not smallest. How can it be smallest? It cannot be smallest. So it has to be largest. So you see that in this case, so basically draw cylinders around each one of them and choose the largest cylinder, because if you don't choose, suppose this cylinder goes through this and like this. So I've taken, this is the largest. So if we don't choose this, if we don't choose this cylinder, then the question is, see, the error at each point must be within X% of full scale or Y% of reading, whichever is larger. So here, if we don't choose this one, then it will certainly fail. If you don't choose the biggest of Xi, then it will certainly fail the X% of reading at this point. But that does not matter. The point is that if it can clear, so suppose this reading, let's rub this reading. Suppose this reading, or let's rub this reading. Suppose this reading was here. Then, suppose this reading was here, and then if I choose X% of this, then it will fail the X%. But who knows? Maybe my Y% of reading cone is like this. Oops. Possibly my Y% of reading cone would have been like this. So even if it had failed the maximum X% reading, I mean, if I choose this, it will fail this, the X% reading, but the Y% reading, it will catch. So the error will still be less than Y% of reading, whichever is larger in that. So therefore, there is no need to choose. Therefore, even a smaller choice of the cylinder will also do. But so we have to find out. So that means this is not the you need not choose the biggest of the Xis as X%. That's not that may not be necessary, because the biggest of the Xis would have been this cylinder. But even with a smaller cylinder, it may match if the Y% of reading cone is bigger. Do you understand my problem? I do not have a solution. I have to think. Did you follow the problem that I was talking about?
Sir, but the minimization will depend like how we are minimizing it, right? Like
that the objective is simple. Objective is that come up with a specification X% of FS, Y% of reading, whichever is bigger is larger. This is my specification. Come up with smallest values of X and Y, smallest possible values of X and Y, such that this every error, E1, E2, E3, all these errors, they all satisfy this specification. So the idea is to have the smallest possible values of X and Y. Because if we increase the X and Y, it is very easy to satisfy that E1, E2, E3, but then the instrument looks very bad. So we are trying to understand that given a calibration experiment data, how we can choose the smallest values of X and Y. Actually, you know, this smallest value of X and Y is also ambiguous, because you may have to trade. That means that you may have to, suppose you have two readings, two specifications. So one is X star, Y star. Another is X plus Y plus. And we have X star as less than X plus, but we have Y plus less than Y star. It's possible. Two possible specifications. In one, the X% of full scale number is better. In the other, the Y% of reading number is better. Means better means smaller. So in that case, it's very difficult to say which one is better. We can always say that if you have two values of, you know, say X star, Y star, and X plus Y plus, two set of specifications, this is worse than this. This is worse if both X star is greater than X plus and Y star is greater than Y plus. That we can say. So then this will not be acceptable. But if we have this situation, this is called Pareto optimal. So you cannot really say. So you are saying one thing is saying 1% of full scale and 2% of reading. Another one is saying 1.5% of full scale and 1.5% of reading. Then it's your engineering judgment, which one you want to choose. It will probably depend on whether you are, it's very difficult to judge. But our question now is, and we'll take it up on Thursday again, because we don't have a problem. So we have got a good problem whose answer right now I'm not sure. I'll think about it. So we have gone way beyond the book now. This is the beauty of the class. We have discovered a problem which is not discussed in the book, and we have to think about it. So please think about it, and we will talk about it in the class. So you see, construction of a specification of an instrument from readings is not trivial. Okay. Recording has stopped. क्या बोल रहा है? Saving recording to OneDrive. Oh, ये already बोल रहा है. अच्छा, okay. So fine. Bye bye then. See you on Thursday.